This is going to be a relatively short lecture, just kind of pulling together the mathematical background we've just established in the last lecture, how to look at one of these geometric patterns, a point group, with symmetry elements that are operators, essentially. We gave the example last time of having a twofold axis with a mirror plane, and we showed that if I have one mirror plane and I have a rotation, I actually end up with another mirror plane that's unique, that's induced by the other elements. And of course, it's a good sign, a good potential for a group, because these two combine to create this one, these two combine to create that one. And we showed in the table about how that's true. There's an identity element and there's an inverse, which is all of these actually are inverses for themselves. And so I end up with a group. Now, that is just showing you that it's a group symmetry element. It can be added to other groups. And that's mathematically what we're doing when we say we want to go in and drop these motifs at lattice planes later and form our crystallographic 2D space groups. We're actually able to kind of drop them in that language because, and we're not going to come back to these identity matrices that often, but it's showing you that when we do those things, it's consistent with group theory and that we're not violating these types of things. And so anytime, what's going to happen is that when we have this case where you're in a group and two elements always induce a third, it's going to be very convenient when we're drawing out these space groups, because we say, aha, I have these two rotations, therefore it always means that when I have these two, it induces another member of the group, and so this has to be here. And we're going to do a lot of that inspection. And when we do that, what I want to show in this lecture, and just tying it all together, is that we're just identifying other elements of the group that have to be there from combination theorems. And we're going to use a simple example, in this case, of the hexagonal group. And we're going to show you that it's got twofold and threefold subgroups, so the subgroups can be superimposed, right? And they're elements of the hexagonal group, and there's additional elements that are introduced. Now, we don't create combination theorems for this trivial case because we've already derived the elements of these groups separately. We've talked about the hexagonal rotation. We know how many angles are there. We've already talked about the twofold and threefold. We're doing it, again, by inspection every time we look at twofold axis, threefold axis, things like that. But the reason I want to go through this is just to show that when we do those operations, we're not just doing them randomly. They're connected to group theory. We're consistent with math from group theory. And that, this isn't cavalier. We're not just like running around throwing things together because we're looking at pretty pictures. Okay? So if we look at the hexagonal group, we see that it has these members, right? It makes sense because I have, lattice point, let's say, with some motif around it, right? And, I rotate the minimum angle that gives me that symmetry here, which is the a 2 pi over 6. And then, I have any combination of these angles. For example, I could rotate 2 of these, which is 2 pi over 6. I could rotate 3 of these, right? If I'm on any one of these points, I could do 3 of them, which is 180, which is 8 pi, etc., right? So all of these allowed rotations that I'm showing you here are in here, right? Because I can do n number of these smaller a2 pi over 6. So here I'm doing 2 of them, 3 of them, 4 of them, and then 5 of them, right? The reason I can't do 6 and create another element is if I go around 6 times, I end up in the same spot, which is 1, which means 1 means nothing's happened, which is our identity element there. So, so basically, these are all the elements inside a 6-fold point group, right? Now let's look at, then I said that we're going to use the example of twofold and threefold. the elements inside a twofold axis are only 2, right? Because if I look here and I have, you know, some motif here, and I rotate around, in this case, 180 degrees, if I do it again, I end up back at 1. So there's only 2 elements because I go round and round. Here, I could do more combinations because the angle's smaller. And so there could be 1 of these, 2 of these, 3 of these, and they always get you to another, you know, point around here, right? Here, because of course it's 180 degrees, I just do 1 operation. If I do more than 1, I just end up with that again. And of course, threefold is in between because if I had some elements here, like say I had this one, that gets rotated. I'm going to actually move it in closer because it's overlapping with the text here. It's going to go over there, and if I did this right, this one would, go over there, right? So if I did this correct, which I think I did, then you can see that motif gets rotated, every time around there. Now, there's 2 possibilities here. I can do 120 degrees, which is an a 2 pi over 3, or I could do 2 of them, and I still get on a symmetry element. So there has to be another rotation of a 4 pi over 6 in there, right? So this one has 3 elements in this point group. So this is a twofold point group, which we've already discussed, and this is a threefold. It's just that we're looking at them as point groups. They're point groups because they're operating around a point A in each one of these cases, right? So now let's look at if I do 2 operations. If I take a twofold and a threefold, again, thinking about doing an operation of a pi on, let's say, already existing a 2 pi over 3, right? Then, which also means operating on a 4 pi over 6. What do I get, right? And, well, if we let's start with this pattern I already drew here for the threefold. What you're going to get is that this guy needs to be, with a twofold axis, he needs to be reproduced over here. Right? This has to be rotated 180 degrees down. This guy has to be rotated 180 degrees over here. And this guy needs to be rotated 180 degrees over here. And so what you can see is that when I take these 2 subgroups, I add them together to make this one, right? I end up not only with all the elements of these groups, but I get additional elements, right? So I could have a combination theorem over here, but I didn't need one because we derived the 6-fold compatibility with the lattice a different way. But you can see here, what's going to happen is that, yes, the twofold operating on a threefold gives me the 6-fold symmetry, right? So it gives me the 1, it gives me the a over pi, it gives me the 2 pi over 3 and the 4 pi over 6. Oops, did I do that? Yeah, oh, this should be 3, by the way. Sorry. 4 pi over 3, right? Which would then be, 8 pi over 6. So the but now I induce these two new ones, which are the smaller angles. So I didn't put this small angle in. I just took a twofold and I operated on the threefold. And I got this hexagonal one, and it induced these two extra elements, showing that the bigger group has extra elements the subgroups didn't have in it, right? That's the same thing as saying last time when I had the twofold axis on top of the mirror, right, plane, it induced that extra mirror plane, right? So it created the other element that we have in the group. And that's useful, again, because when I put two symmetry elements in there and some pattern in the future when we're looking at deriving these things and we see, those two elements are there, it means I have to have this over here, right? So for example, if we were, I won't be doing this, but if we were having a threefold axis and for some reason we decided, let's superimpose a twofold axis on top of it, we would know that we're going to induce smaller angles than are in either one of these alone, although we'll still have these angles as well. So these are subgroups into a larger group, but the larger group has new elements that are induced by these two operations. Okay?